Okay, now I am here to discuss pre-envelopes in the Hilbert transform. So I have made one figure. Now what is this pre-envelope? Now if we talk about a signal in which imaginary part, if we say that is Hilbert transform. Hilbert transform of its real part is known as analytical signal. Now we want to we will use Hilbert transform to define a pre-envelope. How we will do it? It is like g of t. In terms of real signal, it is g of t like this plus sign it is denoted as. In terms of real signal of g of t. The pre-envelope is a complex signal in which imaginary part is the Hilbert transform and Hilbert transform of the real part. Now you can write it g plus of t is equal to g of t plus j of g cap of t, that is imaginary part. Let this be equation number 1. From equation number 1, g cap of t is the Hilbert transform of the given signal of g of t. Let g plus f denote the Fourier transform of g small g plus of t. Now from equation 1 we can write g plus of f is equal to g of f plus of imaginary part g cap of f. Let this be equation number 2. Now the figure, you see this figure, this is a figure. You can see that g of t, small g of t and capital G of g of t is going to g cap of t and g of f is going to g cap of capital G cap of t. So this is passed to the Hilbert transform, which is minus j signum of f, and h of t is equal to 1 of pi t. Now referring to that figure, we can say we can write g cap of f is equal to g of f that is capital H of capital F. So we can write g of f, we all know H of f is minus j signum of f. Let this be equation number 3. Now from you can substitute equation number 3 in equation number 2. So we will get g plus f equal to g of f plus j minus j g of f signum f. This will be written as g of f plus g of f signum f. Let this be 4th equation. We can recall signum f. What was signum f? Equal to 1, 0 and minus 1. 1 was when f was more than 0 and 0 was for f equal to 0 and minus 1 was well f is less than 0. Let this equation be 5th equation. Using the definition of signum f given in the equation number 5, now use equation number 5 in equation number 4. So we will get g plus of f is equal to 2g of f for f is more than 0, g of 0 f is equal to 0, or you can say just g f is less than 0. Let the equation number 6. In order to understand the significance of equation number 6, let g of t be the low pass signal. You can say low pass signal having a spectrum shown. I'll make a figure. This is a spectrum. This is g of 0 here, and this is g of f. This side is capital W minus, and this is W, this is f. This is a spectrum of g of t. Now this is you can say 1.2 figure. So shown in this figure, using equation 6, we plot the spectrum of g plus of t, and it appears to be, this is 2g naught, this is w, this is f, and this is 0. This is a spectrum of pre-envelope g plus of t. You can see the spectrum, so you can mark it as g plus of f here. So pre-envelope. Now this is figure number 1.3. Figure 1.3 indicates the pre-envelope g plus of t has no frequency content for all negative frequency. You can see there for negative frequencies no frequency content. So the spectrum depicted in this figure 1.3, it's non-zero for you can say it is non-zero only for f more than 0. So this justifies the significance of the suffix, like we have done the significance of the suffix plus. So we don't have anything for f more than 0. We have for f more than 0. So only plus it is used. So we can define pre-envelope as g plus of t. Now the spectrum shown in this figure 1.3 indicates that there is no even symmetry about the origin. No even symmetry. Implying that g plus of t is a complex signal, which is the case. In the nutshell, the pre-envelope of g of t can be found as follows, like in time domain, we can say g plus of t is equal to g of t plus j of g cap of t. In frequency domain, using the definition equation from inverse Fourier transform, we can say g plus of t is equal to minus infinity to infinity g plus of f exponential j2 pi ft d of f. Let this equation number 7. Making the use of equation number 6, we can write g plus t equal to 2 minus infinity to infinity g of f exponential j2 pi ft d of f. Let this be 8th equation. For the low pass limited spectrum shown in the previous figure, we can reduce g plus of t equal to 202 w g of f exponential j2 pi ft d of f. Let this be 9th equation. It may be noted that G plus of t defines the pre-envelopes for the positive frequencies. Similarly, we may define for the negative frequency pre-envelope. You can write it as G minus t equal to G of t minus j G cap of t. Let this equation number 10. Taking Fourier transform on both the sides, we will have G minus of f equal to G of f minus j G cap of f. Let this equation be 11. Substituting according to previous equation, G minus f equal to G of f minus j signum f G of f. So you can say G minus of f equal to G of f minus G of f signum of f. This is equal to 0 for f is more than 0. This is G of 0 for f is equal to 0 and 2G of f for f is less than 0. Let this be equation number 12. Let again assume that G of t is a low pass signal having a spectrum as shown in the figure. I'll make a figure for that. This will be like this. In the negative side, this is 2G naught. This is G minus f, this is minus w, this is 0, this is f. So this is a spectrum of G minus of t. From this figure we find that spectrum G of t is non-zero only for negative frequencies. And this justifies the reason for putting suffix negative for the negative pre-envelope G of t. Thank you.